This is a very simple organic molecule. Right now, it has many carbons to you, but if you're going to find out, this is really simple. If you look at later, it has many carbons, and then it also have other elements like nitrogens. It could have oxygen too. Oxygens and nitrogens are also hybridized as well, just like the carbon. But the difference in the nitrogen and oxygen, they come with electron pair, lone pair. Right? Nitrogens are supposed to have a one lone, oxygen are supposed to have a two lone pairs. So we can make questions asking hybridization state, not the carbon, because carbons are very simple. If it's a single bonded, sp3, double bonded, sp2, triple bonded, sp. It's very, very simple. But when we ask the question for nitrogen or the oxygen, it could be tricky. So that's what I'm trying to go over with this example. So first of all, that's what I said. The carbon here, even though we see two lines, you know the line in the drawing doesn't really show the hydrogen. So you're supposed to know these carbons are supposed to have two hydrogen bonded there. These carbons are four bonded, so that means that carbon has to be sp3 hybridized. So that's something that's easy. And this carbon here right now, this carbon is a double bonded with an oxygen. As I mentioned, when you see the double bonded carbon, that's going to be sp2 hybridized. So we can easily say that, yeah, that's sp2 hybridized too. So these parts are pretty simple. And same thing go for this side too. I mean, this is exactly benzene, but same things like that. This carbon here, it's a double bonding with this carbon and a single bonding with that carbon. One hydrogen is supposed to have, well, because it's shorter hydrogen, the line will join. So this carbon is double bonded there, so we can think that that's sp2 hybridized carbon as well. So carbons are pretty simple. Now let's try to look at the nitrogens. This nitrogen there, what's the hybridization state of this nitrogen? So far, for the carbon, we kind of look at how many bonds it makes it. This carbon makes a 4 bond, so we call it sp3 hybridized. This carbon makes a 3 bond, one with oxygen, one with the carbon, one with nitrogens, so we call it sp2. If it's a triple bonded carbon, it will be 2 bond there, so we call it sp hybridized. For this nitrogen, it has a 1, 2, 3 carbon substituted. So does it mean that's sp2? If it's a carbon, we will say that, but one has double bond. But nitrogen is a lone pair, so you cannot forget about the lone pair of nitrogen. I mean, I kindly show the lone pair there, but in often cases I do not. You need to write out what the lone pair is going on by yourself. But that nitrogen lone pair is going to be occupying that orbital, sp, whatever the hybridized orbital. So what that means is this nitrogen should have 4 spaces available. One with a bonding with this carbon, second one bonding with that carbon, third one bonding with this carbon, and then it also needs a space for the lone pair. So it requires 4 slots. So that nitrogen there is only physically 3 bonded there, but it's an sp3 hybridized. Yeah, that's not too bad, right? You just have to consider lone pair as a metal substituents, even though it's not exactly making the same shape as a making bond with the neighboring carbons or other elements. But if you consider lone pairs, you can figure out what's the hybridization of this nitrogen. But I mean, look at that oxygen there. That oxygen is bonded with the carbon with a double bond, right? It has a lone pair, 2 lone pairs, one here, one there. So if you consider the lone pair exists, and then one bond with the carbon, so this oxygen should have 3 slots, 2 for the lone pair, 1 for the main carbon. So that it has to be sp2 hybridized oxygen. Right? So that's a simple. That ends that part. Yeah, you can figure out easily. What about that nitrogen right there? That nitrogen's bonding with this carbon, bonding with that carbon with a single bond, bonding with the hydrogen with that, and has a lone pair. This looks exactly the same as that one. If you only look at this vicinity, right? That looks the same. If that's an sp3, that also has to be 3, right? That's the one who, yes. And the answer is no, it is sp2 hybridized. And this is a question we always ask in the test. And then we always get someone who doesn't answer this right. I don't know why. We keep telling you, I keep stressing out. So I hope that all of you know this, at least for this question. Believe me, I'm going to post this practice test later. You're going to find out this question always appears, even though we already announced that we're going to ask this question. Every year we ask that question. I don't know why you guys missed this one. But now I'm going to explain one more time why it is not sp3, even though this just looks like that. But somehow, this nitrogen is sp2 hybridized, that nitrogen is sp3 hybridized. What makes a difference is the resonance structures. These nitrogen lone pairs cannot make any resonance structures to anywhere. You see, it's a fully occupied, no electric deficiency anywhere. So these lone pairs just has to be stayed on nitrogen 100% of their time. No resonance structures possible. Compared to that, if you look at that nitrogen lone pair, which is this one, if this nitrogen lone pair is having a carbonyl next to it, that allows resonance structures. How we can create the resonance structures? These lone pairs are coming in, make a double bond between this carbon and nitrogen like this. And then this one of the double bond electrons has to go to oxygen that makes an oxygen. This is not the major contributors. This is going to be the minor contributor because of charge separation. But at least the resonance structure is possible. What that means is this nitrogen cannot be sp3 because if it's sp3, that doesn't explain these structures. You may think that looks sp3. Why can that be sp3 and sp2, sp3, sp2 going back and forth, back and forth? Some of you wondering why that's not possible. I would say that I would like to remind you, none of the resonance structures are real. They don't exist this way, they don't exist that way either. This is something that we talked about very first time. None of the resonance structures are real. They're not real form. There's no structure like this, and they're just going back and forth, back and forth. We can kind of explain that way, but that's not how actually they exist. The real structures are in between all these two hypothetical structures. So that nitrogen supposed to have one specific hybridizations, but that should be able to explain this, also explain that. So if you consider these nitrogens as sp3 hybridized because of this resonant form, that doesn't explain these forms. But if you consider these nitrogens as sp2 hybridized because of the one with it, we still can explain that one. How? This nitrogen is sp2 hybridized, then it's supposed to have 3 sp2 orbitals. One make a bond with this, the other make a bond with that, and then the third one is bond maker with a hydrogen. Then where the lone pair is supposed to go, that was the leftover orbital. sp2 hybridized orbital and carbon have 3 sp2 orbitals and then one of the p orbital. So that's the p orbital where this electron pairs goes. So if we consider this sp2 hybridized, we can explain those two resonance structures. So that's basically what it is. This nitrogen, we're going to consider sp2 hybridized, and it actually makes a double bonded characters between those two carbon and nitrogens, even though it looks like a single bond, they truly exist part of double bond in reality. So that's the reason this nitrogen is sp2 hybridized. And then with that question, we also ask which orbital this lone pair reside. And that lone pairs. You can see that these lone pairs in sp3 orbital, right? This nitrogen makes 4 sp3 orbitals. 3 of them make a bond with the carbons. And then the 4th one, that's where the lone pair goes in. So if I ask you which orbital these lone pairs of that nitrogens are in, then you should say sp3 orbital. But that lone pairs, that of nitrogen, is not in sp3 orbital because it's bonded with an sp2. 3 sp2 orbitals are used to make a bond with the 3 atoms. Then what's left over? The p orbital. These lone pairs go to the PO. And that's the one that makes this double bond with this carbon. So you can see that if it comes to the heteroatoms like nitrogens and oxygens, it becomes a little difficult, especially when it makes a resonance structures. So that's something that you gotta be studying for. Look at this aromatic side. The 6-member maybe the double, single, double, single, double. These are aromatic structures like the benzene, even though nitrogen is in the corner. So they're supposed to be like resonance structures. But what I'd like to show here is, sure, we know these carbons are sp2 hybridized. That's sp2 hybridized. And double bonding is created by the p orbital sharing density as a pi bond. That is something that you know already. You can see the structure of the benzene. But this is something called the pyridyl group, the nitrogen here, that's things I'd like to say one more time. This nitrogen, what with the hybridization of this nitrogen, you should pay attention that it makes a double bond with this carbon, right? When you see that, it's simple. If it makes a double bond, gotta be sp2. I mean, sp2 hybridization state typically make a 3 bonds. So we got the 1 bond, this carbon sp2 orbital, another bond with that carbon sp2 orbital, but third one comes out this way because it's a 120 degree bond angle. What's occupying that orbital? It's a lone pair. So if I ask you what orbital this lone pair goes, then you should say sp2 orbital, not the p orbital, right? So depending on what it is, the answer keeps changing it. You got to be analyzing the hybridization state, how they make a bond with each other's. I mean, the bonding is simple. Lone pairs are, it typically goes leftovers, but it also changes depending on what they make the bond with.